So by applying the De Morgan theorem on the Boolean function, you are in a position to convert into any one of the forms which may be suitable for you for some particular application. You look at this, what does this say? This says A bar multiply by B bar and take a complement of that, and similarly take A and B bar and AND it and take a complement of that and put them into another AND gate and take a complement of that. Now there is a gate which I don't know whether I mentioned it or not. This is a normal AND gate. I put a 0 on this at the output, saying that automatically this will give you a complement of the output. This is called the NAND gate. Negative AND gate, and negative in the sense it is complemented. So this is called a NAND gate, and similarly you have an NOR gate also, where you have this is NOR gate. Very extensively NAND gates are used in logic design or logic synthesis, and most of the hardware is available in the form of a NAND gate. And this way of looking at this tells you that any Boolean function in general can be expressed in terms of such form, pi form, and pi form is naturally amenable for NAND operations. So in other words, any Boolean function should be synthesizable by using only NAND gates. So that the power of the NAND gate. So this, what is the circuit for this? Can I erase this? Circuit is A bar B, A B bar, then what do you get here? A bar B bar, because of this automatically a bar comes, and this will be A B bar bar. Now what is to be done with that? These two? I must take an AND of this and a complement of that, which again in AND. So you take these two, put it to an AND gate. This is equal to C. So now you have one form which I wrote to you earlier using only AND gates, another form using NAND gates, and if you use this form you get another set of another type of form which is the OR gate. OR gate ended up with a inversion, or these are OR gates and this is the NAND gate. So two OR gates and one NAND gate also will give you this form which is the pi sigma form. So this is the third way of finding the realization of the logic function. So any one of them according to your convenience, which are gates are available to you, you can use any one of these three forms. But important point I mentioned to you in the last class is which form do you prefer? Here you have three gates. Here also you have three gates, previous one. This also has three gates. So all of them have number of gates or number is equal to same, assuming NAND is or NOR or 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 something is a gate by itself. So we are not looking at the NOT operation. So all of them require the same number of gates. But it may turn out in some other problem, some of this representation may give you lesser number of gates, in which case in some sense you will prefer that implementation rather than the larger number of gates. The second thing is what is important I mentioned to you in the last class is there is invariable delay when you apply A and B bar here, the operation at the output here A, B bar will take some time to happen, which is some kind of a response time of this particular gate. This happens because the transistors which are contained inside, when you apply a pulse like this onto this transistor, it is in cut-off mode and you applied something, so it will take some time for this to reach the value you are looking for. So, the output waveform you must have seen in the lab actually, the output will be something like this, right, and this time that is required to reach this maximum value is called the rise time, and this value is called the fall time. And this is why does it happen? Because for the current to set up in this, when you apply a voltage 1 here, it takes some time for all these charges to form. So, that gives rise to rise time, and the decay time or the so called fall time comes because this is already charged to this level, lot of charges inside, and the charge has to be removed to bring it back to zero condition. And normally it turns out that usually this is a much longer time than this. So, fall time are invariably larger than the rise time. Why? Because the rise time you started the system with a zero condition, there are no charges. So, it takes much faster to reach this final state, whereas in the fall time you have already a lot of charge accumulation is there in the device, and that has to be taken out, and as a result of that this is invariably larger than this. And when we are doing difference amplifier, I mentioned to you that this charge accumulation takes place only because of this devices getting into saturation level. And in the case of diff amp, we never allow it to go into saturation, cut off state, and I mean not cut off, saturated state. As a result of that, the logic which is built out of difference amplifier using BJTs comes out to be having these times much shorter than the any other device, any other topology. So, that is why for highest speed I mentioned to you that the emitter ECL logic, emitter coupled logic is the most frequently used, in which case the total time in that is much less because we are never allowing it to go into saturation point. Okay? But these are matters of detail. So, as a result of this kind of behavior of these active devices, then whatever you put here will take some time to happen here, and again it is something time will take to happen here. So, there is a delay from input to the output depending upon the number of stages of the operation you are doing. In this case, there are 2 stages of operation. In a big circuit, there may be large number of stages of operation, and it may turn out that this output must be ANDed with another output coming from some other circuit here, right? And we are assuming them to be combinatorial logic. Strictly speaking, this is not a combinatorial logic because there is some amount of delay time. It depends upon when after the delay time only it becomes a combinatorial logic. Now, it may turn out if that fellow has a lot of gates in the line and this fellow has 2 gates in the line, that fellow will have a lot of delay, whereas this fellow has a lesser amount of delay. And when you are adding up these two, you are adding wrong values of binary Boolean values, right? It's possible. So, I must design circuits such that at each stage this kind of balanced. This is the synchronous circuits. In other words, not synchronous, I mean the time point of the delay times are kind of made into equal at every point. It's a very tough game to do, because some operation may require more gates, some operation may take less gates, and then to say that both of them should come at the same time is not possible. So, what do we do? The only answer is make this happen at a given instant of time which you pre-decide.